They built this without steel, without engines, without modern concrete, and yet it still stands. The Colosseum is often remembered as a place of spectacle, but beneath the stone and arches lies something far more important. A carefully engineered system designed to lift massive weight, move tens of thousands of people, and survive centuries of stress. This was not brute force, it was Roman engineering. The foundation of the Colosseum begins with materials chosen for specific roles. Travertine limestone formed the outer shell, selected for its strength under compression. Inside, lighter volcanic tuff and brick reduced overall weight while maintaining stability. Binding everything together was Roman concrete opus cementitium. Unlike modern concrete, it relied on lime volcanic ash and aggregate. This mixture hardened slowly, growing stronger over time rather than weaker. Roman builders did not rely on a single material to do everything. They combined materials strategically, assigning each one a task. Strength, where weight was greatest, flexibility, where movement was expected. This layered approach allowed the Colosseum to be massive without being solid and durable without being rigid. The Romans did not lift stone blocks by strength alone. They built machines powered entirely by human effort. Wooden cranes, compound pulleys, and treadwheel hoists multiplied force through geometry. By walking inside large rotating wheels, workers converted body weight into lifting power. These systems allowed a small team to raise stones weighing several tons with precision. Force was not increased by adding more people, but by redirecting effort. Lifting became predictable, repeatable, and controlled. Stones could be positioned exactly where they were needed. Roman construction sites were not chaotic. They were mechanical environments where physics replaced brute force. The true strength of the Colosseum lies in its geometry. Arches form the backbone of the entire structure. Unlike flat beams, arches redirect weight sideways, channeling stress into columns and foundations. This allows massive loads to be supported without solid walls. Layer upon layer, arches and vaults distribute force evenly throughout the building. No single point carries all the weight. This design creates strength through balance. Even when parts of the structure fail, the system remains standing. Roman engineers understood that stability is not about resisting force, but guiding it. Building the Colosseum required more than tools. It required organization on an unprecedented scale. Materials arrived on schedule from quarries across Italy. Labor was divided into specialized teams: cutters, haulers, masons, carpenters. Measurements were standardized, allowing parts to fit without improvisation. Construction followed a repeatable process. Each level mirrored the one below it. This was not trial and error, it was planning. The Colosseum was built like a system nearly 2,000 years before modern industrial methods. The Colosseum was not only engineered to stand, it was engineered to function. 80 entrances fed into a network of corridors and stairways. Radial and vertical circulation allowed tens of thousands of people to enter, find seats, and exit efficiently. Crowd movement was predicted, guided, and controlled. Bottlenecks were minimized through repetition and symmetry. This was architecture designed as infrastructure. The building behaved like a machine, moving people as carefully as it moved stone. The Colosseum has survived earthquakes, fires, and centuries of reuse. Its endurance is not accidental. Roman engineers designed for failure. Damage could occur without total collapse. Arches distribute stress. Concrete absorbs movement. Stone cracks without bringing the system down. The structure adapts rather than resists. That flexibility is why it remains. Longevity was not a byproduct, it was engineered. The Colosseum was never just a monument, it was a demonstration of understanding, of materials, of force, of people. Roman engineers did not rely on miracles, they relied on systems. And that is why, after 2,000 years, their greatest structure still stands.